So there are several ways to calculate the change in enthalpy. 4 of them that we're going to talk about. We're going to talk about stoichiometry and calorimetry today. And then there's something called the flippy thing, which is Hess's law. And then Big Mama, which is delta H, which is the heat of the products minus the heat of the reactants. And then remember that to find the change in enthalpy or in entropy or in Gibbs free energy, that these are all state functions. So there's going to be many ways to solve for these, just depending on what you have. Huh?
What's delta S and delta G?
Delta S is entropy, and delta G is Gibbs free energy. And we're going to talk about that in the second part of this unit. So make sure you have calculators out. Lots of calculations. Okay, so the first thing we're going to look at is through stoichiometry. So consider the combustion of propane. So we have C3H8 plus 5 moles of O2, and it produces 3 moles of CO2 and 4 moles of H2O. And you see that our delta H is negative 2221 kilojoules.
How long did it take? 3 minutes. Not bad.
Marcus says you get a 50 on the test for that. Oh. Okay, so delta H is negative, so what can we say about the energy? It is being what? Released, or it's being released. So our energy is released, which means it is going to be exothermic. And what you'll see a lot of times on the AP exam, it'll say negative 2221 kilojoules per mole. So that's in that reaction. If you look, that is per mole of our propane. So for every 1 C3H8 that burns up or that is combusted, it's negative 221 kilojoules. For every 5 moles of oxygen, it's negative 221 kilojoules. So we're going to say that or assume that the heat comes from the combustion of propane, that all of it comes from there. Calculate delta H, in which 5 grams of propane is burned in excess oxygen at constant pressure. So, start out with what we know. What do we have? We have 5 grams of propane. And we're going to change that to moles of propane. So for every 1 mole of propane, the molar mass of propane is 44.1. And now we got to get that to kilojoules. So for every 1 mole of propane, negative 2,221 kilojoules is released. So if we have 5 grams, how many kilojoules is that? 252 kilojoules. Any questions?
That's delta H.
That is delta H, yes.
Is the K capital?
K?
Yeah.
No, it's lowercase.
Okay.
It's kilo.
Any questions? All right, next. The enthalpy of formation of Na2O is shown below. So what is the amount of heat released when 1 mole of Na2O is formed? So we know that we have, for every 2 moles of Na2O that's being formed, it's negative 828 kilojoules. So if we have 1 mole of Na2O, we know that is negative 828 kilojoules for every 2 moles. Now you're probably going, why did she set that up when I could just divide it? That's fine. So our answer is negative 414 kilojoules. Questions? Answers? Nap time?
Yes.
Nap time, what?
So
Nap time what?
it won't say negative 828 kilojoules per mole.
No.
Because it's for 2 moles in
That would be for the whole reaction, that would be for 4 moles of Na. And that would be for 2 moles of Na2O. So that's why it doesn't say per mole, because it's not exactly one. So
it's not.
it's not per mole, right?
It's just for when it gives you that, it's giving you for the whole.
Mm-hmm. Now we know that it's for one. That is negative 828 kilojoules per 1 mole of oxygen, because oxygen has a assumed 1 in front of it. Okay. All right. The enthalpy for combustion of iron 3 oxide is shown below. What is the enthalpy change for the following reaction? So we have our original reaction, and then what we have here is we have our goal. This is the end product. So what happened from our original to our goal? It reversed. So since we reversed it, then it was endothermic, but now our delta H becomes exothermic. Okay, so if we flip the reaction, we flip the delta H. Kinda, yeah. Well, kinda, because Hess's law, we can add up these reactions together and manipulate it all. All right. Any questions on that? All right, next. Determine the amount of heat released at constant pressure when 1 gram of ethanol is combusted in excess oxygen. Ooh, so now we've got to come up with our reaction. So, ethanol is C2H5OH. It is combusted with oxygen to produce carbon dioxide and water. And I'm going to tell you that the delta H for that reaction is negative 1367 kilojoules per mole. All right, so to balance that, what do we need? We need a 2 here and a 3 there. So that's our reaction. Now we have 1 gram of ethanol, and we need to get that to how many kilojoules per for 1 gram. So if we have 1 gram, and for every 1 mole, there is 46.07 grams. So now we're in moles of ethanol. And we know that for every 1 mole of ethanol, how much heat is given off? Negative 1367 kilojoules. So what do we get? Negative 30?
It's like 29.67.
29 point? Shouldn't it be 297? Is it negative 297? Oh.
Yeah, I don't actually think your equation's balanced. Because you have 3 O's on the left and 7 on the right.
Oh. Yeah, my equation messed up somewhere, didn't it? Hold on.
Color out. Jeez.
You just need to put something in front of the 3.
So, but my problem was my decimal, huh? There's a decimal in there.
Yeah.
Negative 29.7
What?
kilojoules. And that is per gram, right? So if we had, yeah, okay. Any questions on the stoichiometry? It's pretty easy.
How'd we get the 1367 again?
I pulled that out of off my sheet. It was given to. It was given. It's usually given to you. All right. Q equals MCAT. Q equals MC delta T. Q equals MCAT. C is specific heat capacity, and that is of your solution. So the specific heat of your solution or your metal or whatever. M is your mass of your solution, so that's going to be your solute plus your solvent. And then delta T is your change in temperature. And of course, Q is heat. .18. Delta T is change in temperature. We're usually in degrees Celsius, but you don't have to convert it to Kelvin or back to Celsius because it's just a change, and that change should be the same. And temperature, again, always delta is final minus your initial. Everybody good with that? So like I said, a lot of it's review of last year. So here we go. How much heat must be added to change the temperature of 250 grams of water from 25 degrees Celsius to 60 degrees Celsius? So Q equals MC delta T. Our overall goal is to find what Q is. So what's our mass? 250. What is our C? Well, the C, this is in water. So the C of water is 4.18 joules per gram degrees Celsius. And that is on your AP sheet. And our change in temperature is from 25 to 60, so 60 minus 25. So punch that in your calculator and tell me what your Q is.
I got 36,000.
36,575. So we're going to go to 2 sig figs. So 37,000. joules. If you want to put it in kilojoules, then it would be 37. Everybody good with that? Am I going too fast or?
He's still trying to do it by hand.
Okay, let's try the next one. If 2.09 joules are required to change the temperature of 15 grams of mercury by 1 degree Celsius, calculate the specific heat of mercury. So we have Q equals MC delta T, and this time we are trying to find C. So our Q, 2.09 joules. Our mass is 15.0. C is what we're trying to find. And our delta T is 1. So put that in your calculator and solve for C. 0.139. What's our units? J per grams degree Celsius.
What does Q mean?
Heat. Everybody good? All right, let's do another one. We're solving these all different ways, all these different variables. Calculate the final temperature after 1575 joules of heat are removed from an 85 gram sample of ethyl alcohol, originally at 23.5 degrees Celsius. Specific heat of ethanol is 2.4. So Q equals MC delta T. Our Q is 1575 joules. Okay, it says are removed. So that means 1575 is a negative number. Our mass is 85 grams. Our C is 2.4. And we have our temperature final minus our initial, 23.5. So solve for TF. Get me 3 sig figs. 15.8 degrees Celsius. And I went with 3 sig figs because the specific heat is a constant for that at 2.4. So I took 2.4. I didn't take that into account. Any question over that? Do I need a pause? Of in pre-AP, but you're going to see here. So, a 28.4 gram sample of unknown metal was heated to 110 degrees Celsius and plunged into 100 gram sample of water, initially at temperature of 24.60 degrees Celsius. Final temperature of the mixture was 25.34 degrees Celsius. Calculate the specific heat of the metal. and identify the metal. We're not, don't worry about identifying the metal. But we're going to calculate the specific heat. So what do we know? We know the first law of thermodynamics that says that the heat lost is equal to the heat gain. When I see the word lost, I think of negative. So negative Q is equal to our positive Q. What's the formula for Q? MCAT. So negative MCAT is equal to positive MCAT. Just out of habit, always put the metal on the negative side because it's the one that's going to usually be losing the energy. Okay, so our metal, what's the mass of our metal? We have negative 28.4 times the C of the metal, which we're looking for, and our delta T is 25.34. That was the final temperature of both of them, minus the initial temperature of the metal, which was 110. So we took that metal, it was really, really hot, dropped it into the water, and we put it into 100 grams of water. Specific heat capacity of water is 4.18. And then we have the water went from 24.60 Celsius to 25.34. So solve for C. I need 3 sig figs on C. Is it 1 or 0.1? 0.1? 0.129 joules per gram degree Celsius. And that is the C of the metal.
How would we identify that?
You would have a list, or you would go and look for a list through a list and see what specific heat capacity that is. Yes.
Does it matter really degree? Like, could I put GC degree, or is that G degrees?
I always put degree C because you always see degree C when you never see like 32 C degree. But it doesn't matter. Okay, so one thing you need to note here that you can never have a negative C. So you can never have a specific heat capacity that is negative. And you can never have a negative mass. So again, always go back and check your work. Throw that number in there and see if they end up equaling to the same. Any questions on that? Did we do this lab last year when we dropped the metal into the... We did do this lab, didn't we? We dropped the metal into the cup, styrofoam cup of water, and we saw that the metal got really cold really fast. We didn't do that. I could have swore we... No, we did do it because Lizzie and I were talking about it today.
Ooh, might just be
Okay.
because I missed a lot. For some reason, how many days I was absent last year were lab days.
Yeah. All right. So, concept checks, remember that you will not be able to use the calculator on the multiple choice portion of your AP exam. It's because, especially just coal.
They want to kill us. They want to make you kill yourself.
All right, so 100-gram sample of water at 90 degrees Celsius is added to a 100-gram sample of water at 10 degrees Celsius. So we have the same solution. We have the same mass. The only thing that's different is their temperature. So what will the final temperature be when you add these two together? 50 degrees Celsius. Huh? It would be 50. We would take the average of those.
You good there, Andrew?
Oh yeah.
All right.
Was that your therapist? College? Sure. Or a drug dealer?
This time, David,
Sorry.
we have a 100-gram sample of water at 90 degrees Celsius, and we add that to 500 grams of water at 10 degrees Celsius. So our specific heat capacity is still the same, but we add our 100 grams of water to 5 times the mass, and it's a colder temperature. So what is the temperature going to be? C. So it's got to be closer to the colder one, since there's more of it. I mean, you could do Q equals MC delta T. You could see
That won't work because we have a delta now.
delta T. Q. Yeah. Well, you could say what the temperature final. You could say Q. Well, we don't know Q.
negative MK equals positive.
Yeah, that's what I'm saying. Yeah.
Salzburg?
Okay. Next. If you have a styrofoam cup with 50 grams of water at 10 degrees Celsius, and you add a 50-gram iron ball at 90 degrees Celsius to the water, and you have those specific heat capacities, what's the final temperature? So our mass is the same, but we have a specific heat capacities that are very different and the temperatures. So what is going to happen to that temperature? It is going to be C. Okay, so remember, what you need to know is that the bigger your C is, then the smaller your delta T is going to be. Bigger the C, the smaller delta T.
Are we done?
No.
He's been waiting on.
2 days ago, I did might as well just do it now.
All right, and lastly, let's talk about molar heat capacity, or coffee cup calorimetry. Calorimetry.
Your calorie.
It's calorie.
It's full of calories.
So coffee cup calorimetry is just what you have this coffee cup, which is made of styrofoam, and you use it. You've got the thermometer in there, and what you're going to see is we're going to try to find the specific heat capacity, and we're going to use this to try to find our delta H of the reaction. What you'll find is that you might lose some heat to the environment depending on your calorimeter. But what happens is your reaction is occurring to that thermometer. So if your temperature goes up, then in the reaction, then the thermometer is actually absorbing that energy. Okay? So, and then you need to know that there's molar heat capacity as opposed to specific heat. Specific heat is per gram. Molar is per 1 mole. So what you would do here, that is joules per mole degrees Celsius. And you would just convert your mass to moles in Q equals MC delta T.
My mom's boss actually writes her A's as triangles just like that. Just triangles.
Yeah, Marcus, you asked.
Backing up, I'm
Okay, so let's do a problem. When a 1.095 gram of NaOH is dissolved in 150 grams of water at 23.50 grams in a coffee cup calorimeter, the final temperature is found to be 25.320 or degrees Celsius. Calculate the heat liberated when sodium hydroxide dissolves in water. Assume the specific heat of the solution is the same as that of water and no heat is absorbed by the calorimeter. So when you see the keywords, no heat is absorbed by the calorimeter, that should make you happy. That means you know that Q equals MC delta T. So that should make you put a smiley face there, happy that no heat is absorbed. Because we can go straight into MCAT. So what's the mass? We have 1.095 grams of sodium hydroxide, but we've added that to how much water? 150. So our total mass is 151.095. What is our specific heat? 4.18. And our temperature is 25.3 minus 23.50. So what is the Q of this reaction? Or what is the Q here?
Will this heat change because of this?
It says, assume the specific heat of the solution is the same as that of water.
Sorry.
That's right. So what is the Q going on in the cup? To 3 sig figs. So 1,150 joules. Okay, you cannot stop here. That is what is happening. So if we have a coffee cup calorimeter and you have your thermometer in there, that is what is occurring to the thermometer. The thermometer is the one that is absorbing that energy. We want to know what the heat of the reaction is. So you need to take the negative Q to get your heat of your reaction. So our heat of a reaction in this case would be negative 1150 joules. That is one of the biggest mistakes that'll be made on the test, is you will not change that to a negative. Huh? Either one. No, you have to be teaching AP for 3 years, I think, before you can
You're not been teaching for 3 years?
teaching AP Chem.
This is the 30.
This is my second year for AP
Oh,
Chem.
is there a second? Wait, who taught it before?
Miss Coyle.
Who?
She's Miss Coyle.
Wait, so was last year your first year teaching for AP?
No.
Oh,
Okay. Now let's see one that will not make you happy. A 50-gram sample of 0.2 molar sodium bromide at 23.65 degrees Celsius is added to a coffee cup calorimeter. So when you see that word, coffee cup calorimeter, know that you're going to use Q equals MCAT. If the heat capacity of the calorimeter is 65.0 joules per degree Celsius, and the specific heat of the solution is 4.20 joules degrees Celsius. Oh, so now we are not happy because we had two different specific or heat capacities. So the final temperature is 25.4. Calculate the heat release in the reaction. So we cannot go straight into Q equals MCAT. What you have to do here, what this is telling us is that some heat has escaped. Okay? So if it doesn't say there no heat loss, then you're going to have to do an extra step. So here you're going to take the heat that comes from the thermometer, that the thermometer reads, and we're going to add to it the heat that escaped. I can't spell escape today. That is escaped from the reaction. The heat from the thermometer, we just learned, is Q equals MCAT. The heat that escapes from the reaction is Q, and we're going to call this the big C. That is the heat capacity of the calorimeter. So big C, delta T. So we got to find both those answers and add them together.
So what was big C?
Big C is the heat capacity of the calorimeter. So solve for the thermometer first. So our total mass is 50 plus 50, 100. The C of the solution is 4.2. And our delta T is 25.4 minus 23.65. Punch that into the calculator. I got that the Q of the thermometer is 735 joules. All right, but I know that some lost somewhere from the calorimeter, so I need to find the Q of the calorimeter. So now we take the big C, the specific heat the heat capacity of the calorimeter, which it tells us is 65. And again, our change in temperature is the same. So I get 113.75 joules. There, on the heat escape, there's no mass. You're using big C, which is what they tell you, the heat capacity of the calorimeter. That's your big C.
Okay.
All right, so we add those together. So the Q total is what? To 3 sig figs. 849 joules. That is the Q, but we need to know the heat of the reaction, and the delta H of the reaction is negative Q, which means it's negative 849 joules. Okay, so you got to remember, if no heat is lost to the calorimeter, Q equals MCAT. If there is heat loss to the calorimeter, then you need to use Q equals MCAT plus CAT. And then always your final step is negative Q to get your delta H. Any questions?
So, since it asks you how much heat is released,
Mm-hmm.
does that mean